For this tutorial, we will be covering what you need to do to complete Lab 4 homework, aka homework 3. Now we're getting a little off with our numbering, but we're looking at basic ECG reading and energy systems. So to begin, I added all of this small box, large box, 6-second, rhythm, original access, adjustment, and final access. And you can break it down similar. This is a good way to keep track of it and allows you to potentially get a little credit if you screw something up when you're figuring out your access, which is kind of the hardest part of reading an ECG of what you are being asked to do, at least. So to begin with, if you open your lab manual, you will see that on page 49 there's the first step. So method 1 is how many small boxes are between your R to R interval. So this 0.04 here, that represents the time between each of these tiny little lines that we see. And so if I'm using this ECG and I zoom in a little bit more, obviously my lines get a little bit blurry, but it happens. So if I count from here to here, I count 1, 2, 3, 4, 5, 6, 7. Now you can count all of these tiny boxes, or you can look at these more solid lines, and they're harder to see on these ones right now, but if you look for these kind of dots, those represent every 5 small boxes or 1 large box. So if I look at that, that's 1, 2, 3, 4. 4 times 5 small boxes is 20 small boxes. And then I had 2 over here, so I'm at 22, then 23, 24, 25 and a half. And then if I open up a calculator, .02, and if I move that answer down as it says here to do, 60 divided by that number is 58.82. We'll round that up to 59. So 59 beats per minute is what we get using the small box. And this is typically going to be one of your more accurate responses depending what kind of rhythm you have. We'll talk a little more about that when we get down to step 2. If I use the large box method, you might want to find ones that line up better with the boxes versus trying to add a box here or there. So if I go through 1, 2, 3, 4, 5, almost 6. So I'm just going to go with 6 because it's closer to 6 than it is to 5. So I'll go back into my calculator. This time, because the large boxes are 5 of the small boxes, 0.04 times 5 is 0.2. So we're multiplying by 0.2. And we get 1.2 for this one. I'm going to move that down and divide 60 seconds to determine beats per minute. And here it says we have 50 beats per minute. Now we're going to use how many QRS complexes. So this is a QRS complex. There are in 30 seconds. Or sorry, 6 seconds, which is 30 boxes. So I'm going to zoom out. You have to individually count the boxes. I suggest doing it in 5 increments and make 6 of those sets. But so I've counted out 30 boxes of the large boxes, and that's equal to 6 seconds. And what we're going to do is we're going to count how many QRS complexes occur in between those 2 marks. So I have 1, 2, 3, 4, 5, 6. And 6 times 10 because we're looking at 6 seconds when there's 60 seconds in a minute. It's just multiplied by 10 to get 60 beats per minute. So then we move on to our heart, our rhythm. And so at this point, you'd be entering these numbers into your homework for these different values we're getting. So, does your heart rate have a P wave? And the P wave is right here. So you have your QRS, and that's your P wave. So as long as there's this little wave before your QRS complex, then you have a P wave. The chances of you not having a P wave and not knowing about it is very unlikely to occur. If so, talk to your buddies if you think you're missing this P wave, but it's pretty easy to see. It might not be super obvious. Here it's a little smaller obvious than there. So, just for the sake of you being able to see what the thought process is here, I'm going to insert these. Okay, so the next question is, are the R to R intervals? So R is the big spike. Are they even looking at the rhythm strip on the bottom? So I've already inserted this box to kind of show you what I mean. So if I look at this R to R and then move it over, we see that they're not the same. And then if I move it over again, we see that's even a bigger difference. But then when I come over, all of a sudden it's smaller. So for this specific 6 second count, it's not. And as soon as we have that P wave, we're in, and we have this irregular rhythm at the bottom, we're looking at the sinus arrhythmia. Now if I scroll down and do the same thing here, that looks good. That looks good. Again, pretty close. You see overall, it gets a little wide at one point, but then it goes back and it's almost right on again. This would mean that we, yes, are in fact even in our intervals. Now, obviously, we did not count for this with all of our numbers up here, but you'd use these to determine which is best. If you have an even rate and you're in this, you should be using your small box method to determine. Now this 59 is pretty close, but when we use the large box, it's at 50. And even when we did the 6 second count, we got 60, which 60 puts us in normal sinus, but the other two are suggesting it would be a sinus bradycardia. So for this specific one, it is sinus arrhythmia, but if we had that even rhythm across that 6 second count on the bottom, or the rhythm strip on the bottom, we would choose to go that way. Now, step 3 is determining polarity. I'm going to go down to this one to start with. So, what is leads 1 polarity? So, is it positive? So, there's more of this upward spike. Is it biphasic, where there's a fairly equal up and down spike? Or is it more negative? So here we see that it's more up than it is. There's almost no down. This would be a down. So when we look at 1, we see that it is positive. And then we're going to look at AVF. Important thing when you're determining axis is remember you're only looking at these first set of leads, which is why I've already zoomed in so you don't see the other 6 leads to the right, all the V leads. You should be using these first 6 on the left-hand side. So AVF is very positive. Again, And so if both are positive, we can expect our axis to be somewhere down in this quadrant. Now, for this one, it's a little harder to determine which is the most biphasic. And biphasic, again, is the one with most equal up and down. There's not an obvious biphasic lead if you look compared to these other two. This is very biphasic. It goes up and then it goes down, and that's almost equal. Same thing up here. This would be our biphasic lead, which is going to change what you do here a little bit, but you just follow the flow chart, and it's harder to actually gauge your axis if you have a lead that's like this, or all of your leads are looking like this, where there's not an obvious one that is biphasic. So right away, I cancel out 2, 3, AVR, AVF, and I'm left with looking at AVL and 1. From here, if I start from this line, I can see that it goes down about 6 small boxes. If I look up here off the main line, it goes up 4. So I'm going to use this as my main go-to. So I'm going to say lead 1 is my most biphasic lead. Of course, it's not being easy. So I'm looking at lead 1 originally. Then from there, we want to determine which one is perpendicular to this. So find the perpendicular one. And perpendicular to 1 is AVF. So this is going to be what we consider our original axis. That's going to be a plus 90 degrees. And then we have to adjust to see if there's actually any deviation. And in this one, there is. So if I look at how many positive boxes there are off this main line, there's 1, 2, 3, 4. And probably only about 1 negative. So 4 minus 1 is 3. If you have more negative, if these were swapped, it would be a negative 3. So 3 times 5 is 15. And it's positive, so we're going to add 15. So our total degree is going to be a plus 105 degree axis. And that's how we would determine our axis and our adjustment. For number 2, you're just following your lab manual. You should have done this before you left lab. And you're just going to be going down and working down and talking about your percentile based on what you get here. Then, for all subjects who completed Wingate, you need to calculate all these things. So I've entered all the data, and the first thing we need to do is calculate peak power, absolute peak power. So absolute peak power is the first 5 seconds multiplied by 6 multiplied by Kp dropped or added times 12. I forgot my parentheses. And I'm going to divide all of that by 6.1183. And we only need 1 decimal place, 2 decimal places. To determine absolute mean power, we will equal the revolution for the entire bout times 6 times Kp dropped times 2 divided by that 6.1183. For minimum power, we're going to come down here and we're going to look at the revolution, the last 5. times 6 times 12 times the KP added divided by the 6.1183. Our power reserve is going to be our absolute peak power, so this top one, minus the minimum power. Our fatigue index is going to be equal to what we just calculated divided by the absolute peak power. And you don't automatically have to multiply it by 100. I would just simply use the percent sign up here. And I'm going to go in and adjust there. Once you have these calculated, they don't change based on sex, so you can just drag them all over. And then to determine relative peak power, you're just going to take their absolute and divide it by their weight in kilograms. And then the same thing for the relative. And drag them across. So now you have to determine their relative mean power percentile. And so this is based on this first chart. And so these first three are males. And based on their relative, you determine where they are. So first subject, male subject, was at 8.9. So that put him at 15. And then you just go through and do that. For the relative peak power, so make sure for peak power you're looking at the right one. So this is actually the peak power. For the mean power, so for peak, we'd be looking at the 11.47 here. So this person's actually above the 95th. For the mean power, 8.09, they fall right at 85. And then their anaerobic fatigue is going to be the fatigue index. And so this, you want to be on the smaller side. You want to fatigue less. The smaller, the better. So they're at 62%. So that means that this person actually fatigues very quickly. They don't have great potential. So this means they fatigue faster than 95% of the population. But this is how you'd go through this. Make sure you're looking at the right one. I would do all of them for each subject and then move on to the next table so you don't accidentally screw which table is up. And then you'll just finish the rest of your homework. You'd copy and paste what you need from this into a table like we've done in other assignments already and discuss your results. And then you'd finish these last two questions, and that's how you'd complete homework number 3.